In this video, we're going to look at another example of areas between curves. The question here is to find the area of the region bounded by the curves y equals root of 4 minus x squared, which is a semicircle of radius 2, and y equals x squared minus 4, which is a parabola. The first step, like usual, is to find the intersection points of y equals root of 4 minus x squared and y equals x squared minus 4. So let's do some algebra. Y equals y, and solve for x. So we get root of 4 minus x squared is equal to x squared minus 4. The next step is to square both sides. So we get root of 4 minus x squared all squared is equal to x squared minus 4 all squared. So when we square this, the radical disappears and we get 4 minus x squared is equal to x squared minus 4 all squared. Now let's bring everything to one side and we get x squared minus 4 all squared. Subtract 4 minus x squared is equal to 0. Let's distribute the minus sign and it will be easier to factorize it. We get x squared minus 4 all squared, and that's plus x squared minus 4 is equal to 0. If you distribute the minus sign, we get minus 4 plus x squared. All right, now you can see the common factor here is x squared minus 4. So we can factor it out. X squared minus 4 times x squared minus 4 plus 1. This is equal to 0. So we get x squared minus 4 times, and 1 minus 4 is minus 3 times x squared minus 3 is equal to 0. So looking at the first factor, we have x squared minus 4 equals 0. We want to solve for x. Bring the 4 to the other side. We get x squared equals 4. Take the radical of both sides. We get root of x squared is equal to root of 4. Root of x squared is not x, it's absolute value of x. Absolute value of x is equal to 2. Solve for x, we get x equals 2. X equals minus 2. Now, let's look at x squared minus 3 equals 0. Similarly, if we solve that, we're going to get x is equal to plus or minus root 3. We're going to end up rejecting this, and we'll show on the next page why that is. But we will accept this one, x equals 2 and x equals minus 2, as the points of intersection. All right, so what we have is, let's look at the x-intercepts as well. Y is equal to root of 4 minus x squared. And if we look at the x-intercepts, we'll see that's precisely where they intersect. In fact, those are the intersection points. Make this equal to 0. Square both sides, and we get 4 minus x squared equal to 0. We get x squared equals 4. Bring the 4 to the other side. And if you solve this, you get x equals plus or minus 2. Now for the parabola, y is equal to x squared minus 4. We want to find the x-intercept. That means make y equals 0. So we get x squared equals 4. Solve for x, and we get x is equal to plus or minus 2. They share the same x-intercepts. The semicircle and the parabola have the same x-intercept. Those are the points of intersection. Now we're going to show why we reject x equals plus or minus root 3. So oftentimes when you solve this algebraically, you might get some values that have to be rejected. The only way is to plug them back into the functions to see if they have the same y value. If you plug x equals root 3 into the semicircle, y is equal to root of 4 minus x squared. We get root of 4 minus root 3 squared is 3. That's root of 1, which is equal to 1. If you plug x equals root 3 into the parabola, y is equal to x squared minus 4. Plug this in, and we get root 3 squared as 3 minus 4 equals negative 1. These are not equal. That's why we reject it. That's why we reject x equals root 3 and also x equals minus root 3. Not equal. So similarly, x equals negative root 3 by the same reasoning is also rejected. So the only intersection points of the two functions y equals root of 4 minus x squared and y equals x squared minus 4, the only intersection points are negative 2, 0 and 2, 0, which are the x-intercepts of both functions. All right, so now we have to sketch the bounded region, y equals root of 4 minus x squared and y equals x squared minus 4. You can see the y equals root of 4 minus x squared is just a semicircle of radius 2. We're going to show that later, of course. So this here is y is equal to root of 4 minus x squared. And the bottom function is the parabola y equals x squared that's been vertically shifted downwards 4 units. So we get y is equal to x squared minus 4. That is the bottom function. If we draw a typical rectangular slice, the height of this rectangular slice will be, the height will be root of 4 minus x squared, the top function, minus the bottom function, which is x squared minus 4. And the width is dx. And we basically add up these slices in the x direction to find the whole area. So that's dx, and the differential area is going to be top y value minus bottom y value. So that's going to be root of 4 minus x squared minus x squared minus 4, close bracket, dx. So notice the top point of contact right here is with y equals root of 4 minus x squared. The bottom point of contact of the rectangular element is y equals x squared minus 4. And so always this is, you have to do top minus bottom, more minus less. So dA is equal to y top minus y bottom dx. And this ensures that the area comes out as a positive quantities because you're basically adding up these rectangular differential areas that have positive values. All right, so now we have to set up a definite integral to find the area and to solve. So what we have is integral from minus 2 to 2, root of 4 minus x squared minus x squared minus 4 dx. Let's split up the integrals, so area, and then evaluate them separately. Area is equal to minus 2 to 2, root of 4 minus x squared dx minus integral from minus 2 to 2, x squared minus 4 dx. Now looking at the first integral, it is possible that we can use trigonometric substitution with x equals 2 sine theta. X equals 2 sine theta and do a trig sub, but that's too much work. We don't want to do that. We recognize that the integrand, root of 4 minus x squared, is in fact the top half of a circle of radius 2. In fact, it's a semicircle. So the area can be simply found by finding the area of the circle of radius 2 and dividing it by 2. We're going to do that. So area is equal to pi times radius, which is 2, all squared, divided by 2. And that saves us the work of having to do trigonometric substitution, which would take a lot of time. So now this integral will be really easy. That's just reversing the power rule. What is integral of x squared? That's x cubed divided by 3. And what's the integral of a constant? Integral of 4 is just 4x. Evaluated from minus 2 to 2. Apply fundamental theorem of calculus. Area is equal to 2 squared is 4 over 2. That's 2 pi. Minus. Put the upper limit in. The upper limit is 2 cubed. That's 8 over 3. Minus 8. Minus, applying fundamental theorem of calculus, put a lower limit in, we get minus 2 cubed is minus 8. Divide by 3, minus 4 times minus 2, plus 8. All right, let's simplify this. So area is equal to 2 pi minus. Now we got 8 thirds, minus minus is plus, so 8 thirds plus 8 thirds will give us 16 over 3. And we have minus 8 distributing the minus, we get minus 16. If we add this, we're going to get 2 pi, I should say if we subtract this, minus 3 goes into 3 one times, you get 16, minus 1 goes into 3 times, 3 times 16 is 48, 16 minus 48 is minus 32. So the result will be 2 pi minus 32, that's plus 32, over 3. Let me write it here, 2 pi plus 32 over 3 is a result of the area. If you were to decimalize this, it would come to approximately 16.95. Approximately 16.95 for this area. And let me show that on the diagram. So essentially, we find this area to be approximately 16.95. The exact value, of course, is 2 pi plus 32 over 3. Now, let's review a little bit of the integration that we did. So let's look at an integral of this sort, from minus r to r, root of r squared minus x squared dx. Now, we can definitely do trig substitution, let x equals r sine theta, and differentiate both sides and draw triangles. But trig substitution is a lot of work, and we don't need to do it here. So we're going to do, let's do a trick to make this easier. We will notice that y is equal to root of r squared minus x squared is a semicircle of radius r. It's in fact top half of a circle. Why is that? Let's prove that. Top half of circle. In terms of a diagram, it's basically like this. From minus r to r, let's label this as the x-axis, y-axis, that's our origin. So the reason is because we can square both sides. We get y squared is equal to root of r squared minus x squared, all squared. We get y squared. The radical disappears. We get y squared is equal to r squared minus x squared. And bring the x squared to the left-hand side. We get x squared plus y squared equals r squared. This is the equation of a circle of radius r. This is a circle of radius r. That means y equals root of r squared minus x squared is the equation of the top half of a circle. So the integral from minus r to r of root of r squared minus x squared dx, this is simply going to be the area of a circle divided by 2, essentially the area of a semicircle. So it's going to pi r squared, the area of a full circle of radius r, divided by 2. So that saves us a bit of time if we're doing this in a quiz or a test. All right, thank you.